Next, we will see different types of operations. So here, different type of operations of a CPU or a processor is being defined in terms of like data transfer operations, arithmetic operations, logical operations, conversion. Different type of conversions are there. Input output up related operations, system control related, or transfer to control, transfer of control instructions. So we will go by these instructions one by one, or these operations one by one. So these are data transfer operations. So as the name suggests, it is data transfer, means it will be transferring a data from one location to another location. So data transfer will be related to like that. So it is like one, suppose a register is there and here a memory location is there. So between a register to memory or between memory to register, it will be transferring the data. Either it can transfer between two registers also. So between a register, from a register and to a register. So data transfer is like whatever the data is there located at one place, it will be moving the data to another location. Arithmetic operations. So in arithmetic operations, different mathematical arithmetical operations being performed by this computer system. So we will be seeing what different type of operations they will be performing. In the terms of logical operations, so in terms of logical operation, we will be seeing like what is AND, OR, and XOR, NOT. These are the logical operations. We will see that. Conversion. In terms of conversion, we are going to have different types of instructions, like we are converting from one format to another format. So we will see that input output operations. So here basically the operations will be taking place between an input output device to the memory of the processor. Okay, so here for input and output related operations, there is a separate set of instructions defined in each of the CPU organizations. So we will see that like what a different type of input output related instructions are there. We will see one by one. And system control and transfer of control. So system control in the sense like for controlling different operations of the CPU, there is some system control related operations are there. For control system, transfer of control is based on like different instructions are there for transferring the control to a particular device, peripheral device. So these are basically used in case of DMA, peripheral device, when it wants to uh, operate something, want to perform some operation on a particular peripheral by transferring the data. So there the control of the CPU is basically given to the DMA. So it will be transfer of control. So for controlling the transfer, there is a separate instruction. So all we will see one by one. So based on the different type of operations, like different type of operations that a CPU or a microprocessor can perform, these different operations, based on these operations, there will be a separate instructions. Okay, so all set of instructions will be defined in terms of these three types. So different instructions can be compromised or can be included into these three types. So here types of instruction. So in terms of types of instruction, we will be having like a data transfer instruction, data manipulation instruction, program control instructions. So data transfer instructions, it will be the instructions that are going to transfer the data from one location to another location. So based on the different operations that a microprocessor can perform, we will be dividing these operations into an instruction, and these all operations can be included into these three type of instructions basically. So in data transfer operations, we will be moving to have different instructions. So here move, load, store, exchange, input, output, push, pop, etc. There are different data transfer instructions. So we will see one by one what these are basically. Next one is data manipulation instructions. So basically there are the different types of instructions. What different type of instructions can be there? It is divided like that. So next one is data manipulation. So once a data is there, we will be performing some operation on that data, that will be called as data manipulation instructions. Under this, Some arithmetical operations will be there, some logical operations will be there, and conversion of related operations will be there. In program control instructions, here to execute a program, there are different control signals we will be using. These are like a jump, branching and loops, and call and return. They are different program control instructions are there that will be controlling the program with these instructions based on like requirement. We will be using either jump, branching, or looping, or call and return type of instructions. So we will see that also. Okay, so we will start with like data transfer related operations. So here in this data transfer related operations, the instructions will be defined such that it will be having a source, it will be having a destination, and also the amount of data that need to be transferred. Okay, or what data need to be transferred, it should be there. So these instructions should be including this type of points so that it can perform a particular operation. Maybe different instructions for different movements. So based on different instructions, based on different type of movements, we can have different instructions. So and also based on different type of systems. So like if it is, for example, it is given IBM 370, if it is a type of system architecture that is going to use a particular instruction. So these whatever instructions we are going to study here basically will be like its mnemonics or its representation can be different in case of different type of CPU that is being defined. So it is not like fixed. Only the operation will be fixed. Like it will be having data transfer related operations. Like we have seen different move, store, and exchange operations will be there. But for move, so it's like move for move. What it should be like naming, what it names or what its mnemonics will be there. That will be different in case of different type of systems or different type of architectures of the CPU. Okay, but the core idea will be to have a movement from one location to another location, but its representation can be different. Okay. One instruction and different addresses. So in case of like some of the data transfer instructions are there that are like one instructions will be there, but it will be using different addresses. So we can just say, so here for an example, we will be considering the instruction move. So if instead of complete writing move, we will be writing move. If it is two address type instructions, so we will be calling it move A comma B. Okay, so its meaning is we are going to put the content of B into A. Okay, so we are going to move the content of B into A. Similarly, this was the one representation. Another representation could be like instead of the data that is stored into register, we are going to store the data directly into the instruction itself. At that time, the move will be considered as MVI. That is A comma suppose 05 H we want to transfer to A, so it will be represented by this. So when we are going to use direct data, this type of instructions are called immediate instructions. That's why instead of move writing move, we will be writing MVI, that is move immediate. So this we will come across while studying the addressing modes. So these two are different types of addressing modes. So our main theme is to move the data. So how this data transfer basically takes place is, so we know the architecture of the CPU basically, like there will be a memory and there will be some input output devices and there will be some registers. So in registers, there will be different type of register. In memory, different locations will be there. In input output devices, it will be either taking the data or sending the data to the CPU. So when we are going to move the data from one location to another location, we will be going to use the move instruction. So here for moving the data, we suppose this is the location, memory location X. Okay. So with respect to that, if we want to move the data, so instead of this move a comma m is used. So this m stands for memory. So this memory location will be this. So from the memory location that is represented by x, okay, this x will be stored into m, and this from m location to we will be moving to a particular register A. Suppose this is the register A. So from this location we are moving the data to register A. This instruction is similar to that. If we are going to move like m comma A, in that case from A to this location we will be moving the data, or we can directly move the data in terms of input and output. So between input and input output and memory there is some different set of instructions that basically used to move the data from a memory location and then to input output devices, or from input output devices to the memory location. So these instructions are basically called in and out instruction. So for input and output, so if processor wants to take some data from the input devices or input peripherals, it will be using input and then its address. So input and then its address. So input is the instruction and its address will be the location. So from this address location, it will be taking the data and storing to the memory location. Similarly, if it wants to transfer some data from the memory location to the input output devices, it will be using the instruction called out. It will be using the out. So it will be out and then the address location, at which address location this data should be out. So in that case, the by default here we are having one address type of instruction. So here another address is by default the accumulator. So accumulator will be here considered as the default source, you can say. So in case of out, accumulator content will be placed to this location. In case of input, the from this address, the data from this address will be placed to the accumulator. So we can just write here. So here accumulator to a particular location that will be transferred. In case of in instruction, from a particular location to the accumulator, the data transfer will be taking place. So this is in and out for basically moving the data from one location to another. Okay, so this was the move instruction. Another one is like load. So in terms of load, what is there basically is, so basically these are the different types of instructions that we will be going to use while moving the content from one location to another location. So in case of load, so basically this load is represented by like LD, or we can in sometimes it will be like used in as LD, or in some of the architectures of the CPU or the processor, it may be using directly the load. So once we are going to have the load, after that we will be using some registers like load R1 comma R2. Okay, so if load R1 comma R2 means it will be loading the R1 from the R2. Suppose it wants to load the data from a memory location to the R1, then it will be like some memory location, suppose X is the memory location, it will be taking the data from X memory location to the R1. So these are how the load is used. Store in the sense here, for store, it will be like for storing, it is basically instead of store, or it can use STO directly. So it will be like from R1 comma R2. So store means from R1 it will be storing the data to R2, or sometimes if it is like STO only R1 is written, that means it is of one address type of instruction. So here by default the second address is the accumulator. So its meaning will be the data will be loading from accumulator to R1 location. It is storing to a particular location. Load means loading to the system. So loading to R1, like from R2 it is loading to R1, but storing means from this one to a particular location there. So this is load and store basically. Exchange. So there is a separate instruction for exchange. So XCHG is a separate instruction. So here exchange a particular point is like given R1 comma R2. So this is basically used in case of swapping. If we want to swap data between two registers, we will be using the exchange. So its meaning is like whatever the content of R1 is there, that will be moved to R2, and whatever the content of R2 is there, that will be moved to R1. So this input and output instructions are in short form. It is written like in and out. So these are the input and output related operations we have already seen, and push and pop. So in case of stack related operations, we will see what is push and pop. So basically this push and pop is used in case of stack related operations. So there will be an stack memory is there. So in case of stack, we will be using different. So if we are going to use stack for instructions, we will be using only the pop and push. So pop and push are the only instructions that will be using stack for their operation. So here there will be a stack pointer. So when we want to push some data to the stack, we will be using the push instruction. If we want to take some data from the stack, we will be using the pop instruction. So this stack related operations, we will see that later into detail. Okay. So these are the different type of data transfer related operations. Next we will see is arithmetic operations or arithmetic instructions. So in case of arithmetic instructions, basically it is going to perform like add, subtract, multiply, divide, and also it will be like increment and decrement and negate. So these are different arithmetic type of instructions are there. So here add. So in terms of add, there are different types of add. So it's like, first of all, this is add, or we will be writing like, instead of that we can write like ADD capital. So this is if given it's, if it is given like R1 comma R2. So its meaning is R1 plus R2 will be added and it will be stored in R1. This is two address type of instruction. So we have gone through the different type of addresses and their instruction definition or different formats in the previous class. So different, I think you should be able to identify. It is two address type of instructions. The third one, that is destination, will be this one itself. This is add. Sometimes we will be giving the data immediately. Then it will be like ADI. So ADI stands for R1 comma 05. So immediately we have given the data. Instead of data in terms of register, we are directly going to give the data. At that time, this add instruction will be defined by ADI. This is data. Whenever, first of all, when it's like 2, you can say like 5 is there and 0 is there. This is a 1 byte instruction, 1 byte data is there. So it will always be considered as the data. So when we are representing like 1505 H, then this will be the address. Okay. So because address will be represented in 6. So basically we are taking an example. So whenever it will be like address, it will be first of all, if we are having an address, what happens? So if an address is defined like 1505, so we need to, once we want to take data from this location, then we should be defining it like that. That means address in bracket, that means at this location whatever data we are talking about. So here it is like 05. So 05 will be considered as the data itself. Okay. So once we are going based on the architecture of the CPU, that will be clearly visible. Like if 8085 processor is there. Okay. In 8085, suppose we are studying 8085. In there, the data bit is basically of 8-bit, and address based data bits or data lines are 8-bit, and address lines are of 16-bit. So if suppose we are talking about 8085, in that case it will be specific. If 05 is given, that means it is of 8 bit, so it will be a data. If it is talking about like if it is ADI or ADC or even ADI is there, R1 comma 1505H is given. So in that case, this is talking about the address. So whatever instructions we are writing, as I told you, like if a particular architecture is given and we are going to study that particular architecture, and in that case, you will be able to identify what it is basically. Here I have just given an example, like if add is there, normal add is there, it will be like R1 and R2 we will be writing between two registers. If ADI is given, that means I stands for immediate. Immediate in the sense like data is immediately given into this instruction. So in that case, it will be 05H means 05 will be a data. If it is add R1 comma 1505H, so in that case, here we will be talking about like ADI is not given. ADI stands for immediate data is given. If add R1 comma 1505H is given, that means it is an address. As immediate addressing is not available, not given. Okay. So if into this instruction, if immediate addressing is not given, then we will be talking about this is an address. If ADI, that means immediate is, it is talking about an immediate instruction, that means this one is data. So about this addressing modes, we will see the next topic is the addressing mode. So I'm just giving you out different overview, like in terms of add, what different types of add instructions are there. So add is not a single instruction, or subtract is not a single instruction. It will be having different variations of this add or subtract instruction. Even in case of move, we have seen different type of move instructions are there. Okay, so based on the different addressing modes, the instruction types will be different, but their main motive will be to add the data. Okay, but either it is going to add two data, or it is going to add two registers, or it is going to add data from register to a memory location. So it depends. So based on these are called addressing modes. It is called register addressing mode. Here both the operands are registers. This is called immediate addressing mode because immediately data is given. This is called indirect addressing mode. So we will just see that later as we will be moving. Our main motive here is what different types of add instructions can be possible. We are just seeing this. Okay. So I hope you have got the point. And this ADC. So again, if it is ADC, that means add with carry. If add ADC is given, that means it is going to add with carry. Suppose R1 comma R2 is there. So what this will be talking about is it will be going to add R1 plus R2 along with the carry. Whatever bit is stored into the carry register, that will be used to add, and after that the result will be saved into R1 register. This ADC will be talking about.
Okay, sir.
Yes. So also suppose if this is the instruction, so what will be instruction format? So we have seen already. So in case of instruction format, first of all, it will be talking about the mode. So this mode is nothing but the addressing mode. So it will be talking about which type of addressing mode is being used. Okay. Then it will be talking about the opcode. So opcode will be like what operation it is going to perform. So here in case of this one instance, suppose we are having this instruction. For this, we are going to give the instruction format. So for this instruction, the instruction format is basically there will be an addressing mode. This will be opcode means what operation it is going to perform, and then there will be along with the operation it will be talking about the operand, what different operands are there. So it is R1 and R2. So these are operand. Here are the different operands. So in case of operands, so if it is this operand is there, so we can just instead of this, we can just see like we can directly write here operand. This is the general format. In that operand, there could be three different operand. One will be the destination, second will be the source, third will be the source. So if destination, source and source is given, then this will be called as three address type of instruction. If only two addresses are given like R1 and R2, so it is given like one destination is there and one source is there. So in case of two, it will be like only this will be the case. Operand can be divided into two only. If one type of one address type of instruction is there, then only there will be only one operand. Okay, so that will be one operand. We can consider it as source and sorry, it will be the source. Okay, and destination will be the accumulator in that case. So there are different types of addresses that can be used in an instruction. Based on that, we have divided different type of instructions. So each of this instruction add can be represented in either of the addressing mode. Either it could be one address, two address, three address, or whatever. Okay, so that we have already seen, and this is how we can differentiate between different instructions. So inside add operation, we have different type of add instructions. Similarly, in case of subtract, we will be instead of subtract, we will be writing like sub. Then here sui will be the for immediate, suc will be for subtract with carry. So instead of carry it will be a borrow. Okay, so this is how we do the arithmetic operations. Similarly, in case of multiply and divide also, we will be using mul and div as the different instructions, and for subtract it will be sub as the instruction. Along with that, we can use this instruction as one address, two address, or three address. And always here, like we can do the operations either on signed integer or even on floating point numbers. Okay, so this about floating point number, we will see that into the second lecture, second unit. Basically, it is all about the floating point representation, how we will be representing. So based on the data type or data type that we are going to use, so either signed integers are there or floating point integers are there. On these representations, the add and subtract operations will be going to take place. And also it include increment and decrement and negate. So for increment, I and C is called. So if I and C is there, then it will be after I and C, we need to use the register, whatever register is there. So I and C means it is going to increase the content of this register by 1. So it is basically increment by 1. It is plus 1. Okay. The next one is decrement. So it is DCR, that is used instruction. And if it is a register DCR, that means it will be decreasing the content of this register by 1. It will be decreasing the content by 1 and increasing the content by 1. Negate in the sense like whatever the content of the register is there, it will be making its complement. Okay. So these are like the basics of arithmetic instructions. So all these instructions we will see once we will be going to study the assembly language programming. Basically, in that we will be using these instructions basically, and there you will be basically able to use like how these instructions can be used practically. So in terms of assembly language programming, we will see that. Okay. Next one is logical instructions. So basically here, in terms of logical operations, it is bitwise operations. So here, suppose register is there, its content is 0001 1001. Okay, another register, suppose R2 is there, this is R1, and R2 1001 1000. if these two are the content of a register, and if we are going to use a particular logical operation on each of the bit of this register content, then it will be considered as the bitwise operation. So here in case of logical operations or logical instructions, basically it is going to have the bitwise operation. It will be performing the operation. If we are going to have an AND operation, so for that A and D will be used. So A and D R1 comma R2. Okay, so after R1 comma R2, it is going to store the result into the R1 itself. So it is going to have the AND operation. So it will be like 1 and with 0, it will be 0, 0, 0, and with 0, 0 and 0, it will be 0, 1 and 1 and will be 1, 1 and 1 will be 1, 0 and 0 will be like 0, 0 and 0 will be 0, and 1 and 0 will be 0. So after doing the AND operation, we will be getting the result this way, and this result will be stored in, with respect to this instruction, result will be stored in R1 content. Okay, so basically in terms of the bitwise operations, it is going to do the operation in terms of bits available to that particular location at that particular memory location, or from the bits available into that particular register. So what about the logical operation? What this logical operation is called? How you will be explaining the logical operations? So in case of logical operations, it will be like whatever the and we have suppose done, and we are going to perform. So its output will be of Boolean nature, or it will be either 0 or 1. Okay, in case of logical operations. So in case of bitwise operations, it will be like if it is 8-bit data is there, then its result will be also 8-bit data in case of bitwise operation. But in case of logical operation, whatever bit operation is we are going to perform, it will be having either 0 output or 1 output. So this type of logical operations are basically not performed. Only the bitwise operations of this operations are being performed with respect to the CPU operations basically. So we are going to perform the bitwise operations in terms of the arithmetic or logical operations we are going to have. So if a data is given, we will be performing the bitwise operations only. Okay. So this is like how the bitwise operations is basically performed. So in case of AND, it will be like R1 comma R2 will be taking the AND of the data. Similarly, OR we are having, so if it is R1 comma R2, OR operation is there, so we will be performing the OR operation. So in case of OR operation, we will be taking OR of this bit and this bit, MSB together and MSB together. Okay, so 1 OR with 0, it will be 1. 0 OR with 0 will be 0. 0 OR with 0 will be 0. 1 with OR with 1 will be 1. 1 OR with 1 is 1. Again 0 is 0. 0 OR with 0 is 0. 1 OR with 0 is 1. So this will be the OR operation. Similarly, there is NOT operation. So it is NOT is similar to, you can say, this negate operation. Okay. So in terms of NOT, suppose NOT R1 is there. So we are going to take this R1 NOT, means it will be inverted. All the bits will be inverted. So it is 0, 0, 0, 1. So after doing the NOT operation, we will be having 0, 1, 1, 1. So this will be the invert NOT or complement operation. Okay. XOR, similar to that, XOR operation is there. Wherever there will be a difference of bits, that will be 1, otherwise 0. So this is how different logical operations are being performed at a CPU. Next one is clear. So clear stands for like whatever the CLR is the representation. CLR R1 is supposed written. So if R1 data is 10010001, if this is the R1 data, So once we will be performing the clear R1, that means the result after performing this, the result will be all the bits will be cleared. So like in terms of flip-flops, so you might be knowing the different types of flip-flops. So like here, D is the input, Q and Q bar is the output. This is called clock, and there is a clear button and there is a preset button. Clear and preset. So in case of flip-flops, we know it stores 1 bit of a data. So here, if we are going to store 1 bit, that will be stored with respect to D input. So D will be input, output will be Q or Q bar. So if Q and Q bar are called complement outputs. So when whatever the data is stored into this flip-flop is a memory, suppose 0 is stored into this flip-flop. And at that time, we are going to give this clear signal as 0. This clear will be activated. So clear is 0, then the clear signal will be activated. At that time, the output of the flip-flop will be 0. If the, this was the input, or that you can consider like output of the CPU, out of the output of the flip-flop. So output of the flip-flop is suppose 0. If we do the clear, it will be making it 0. If the output of the flip-flop is 1, then again we are going to make the clear signal as 0. Then output will be switching to clear 0. So whenever we are going to do the clear, it will be resetting the value of the register content. It is similar to the clear signal that is activated inside the flip-flop. The same is clear carry. So clear carry in the sense, so we have seen like what is flag registers. So in that flag register, there are different types of carry: auxiliary carry and normal carry, and then sign bit, 0 bit, okay, parity check. All these are the different bits are there. So in that there is a carry register is there, okay, that basically stores 1 bit of information. So in that we can directly clear the content of the carry. If content of the carry, whatever it is there, once we run clear carry CLRC, there will be direct reset of the carry flag. So it is CLRC. So for CLRC, there is no need of inputs because it is directly going to clear the content of the carry register. So there is no need to have some input or operand. So that's why these are called implicit type of instructions. Implicit type of instructions. Okay. Set carry is another one. STC. So STC is set carry means it is going to make the carry flag as 1. In case of clear carry, it is going to make the carry flag CY is equals to 0. Complement carry means CMC. So CMC is complement carry. So if the content of carry is suppose 1 initially, then after performing this, it will be going to convert it to 0. Or if it is 0, then it will be converted to 1. So it is going to complement the carry. So whatever the content of the carry will be there, it will be complemented. So it will be CMC is complement carry. So these three are called the implicit type of instructions. Implicit instructions means there is no requirement of operand, or we can say like operands are clearly defined inside the instruction itself. There is no need of operand from outside. Next logical instructions are like enable interrupt and disable interrupt. So here there is an enable interrupt instruction is there. So once it is enabled, it means all the interrupts. So interrupts are the basically interrupts are the basically you can say once CPU is going to operate, or is basically processor is basically performing some operation, then once interrupt is activated, whatever the operation CPU is performing, it will be completing that in that instruction, and after completion of that instruction, it has to switch to a particular location of this interrupt for temporary operation. That will be a set of some service routine are there. Interrupt service routines are called. So it will be the program execution will be moving to a particular interrupt service routine. Whatever interrupt service routine content are there and instructions are there, the CPU will be performing that operations, and then it will be moving back to the program. So interrupts are basically the in interruption in execution of the regular program by to the CPU or to the processor. Uh, Basically, it is going to operate some instructions located at particular location. That instructions set of instructions are called interrupt service routines. Okay. So that can only be possible when the interrupt are enabled. So there are different types of interrupts. If interrupt enable pin, or we can say like if interrupt is not enabled, then there will be no interrupting the CPU operation. So once the interrupt is enabled, then only all possible interrupts are there. They will be able to interrupt the CPU operation only when interrupt is enabled. So there is an EI instruction. It is also implicit type of instruction. It is not requiring any input or operand to operate. So once it is activated, it is going to enable the interrupt. It will be enable the it will be basically enabling the, and similar to that there is a disable interrupt. So it is going to disable the interrupt. So once disable interrupt is run by the CPU, the processor, then all the interrupts will be disabled. Once they are activated, or like they are they want to interrupt the processor, they will not be able to interrupt because all the interrupts have been disabled. So these are the different set of logical instructions. Okay, some other logical operations are there that are called shift operation. So in case of shift operation and rotate operations, there are different type of shift and rotate operations. So we will see these instructions one by one. Okay, so I think you might be able to these written contents are visible. I think logical right shift, logical left shift, arithmetic right shift, arithmetic left shift, right rotate, left rotate. Okay, so we will see one by one what these are basically. So here logical right shift. So what is the meaning of logical right shift? Is like, as it is indicating, if it is a register, inside some data will be there. All the data will be shifting to the right side. So we'll be taking some examples. Okay, so we'll just take an example. Suppose this is an register content. So it is suppose 0 1 0 0 1 1 0 0. If this is the content of the register, if we want to have logical right shift, logical right shift means we need to shift it the right side. So after shifting to right side, the content will be like So after shifting it, we'll just see like what is the content moving. So if it is right shift, this last bit data will be moving here, will be 0. This one will be moving here, 1. This is going to move here, 0. They will be shifting right side, 0, 1, 1. This one will, 0 will be shifting to this 0. And this data will be discarded. And here, one bit will be left with because there is no data to be shifted. So here by default we will be putting 0. So we will be writing it 0 with a special color. So we are going to add it 0. So it is directly shifting all the data to the right side. So LSB data will be discarded, and in the obtained result, the MSB data will be vacant. So here we will be putting 0, including the 0 one. Okay. The next we will see, this is called the right shift, or this is logical right shift. Next we will see is logical left shift. So in case of logical left shift, suppose this is the register. For an example, we have taken an 8-bit register. So suppose 1 0 1 0 1 1 1. Okay, so if this is the content, we want to have logical left shift. So we are going to shift the data to the left side. So after shifting to the left side, what will be the content? We'll just see. So once we are going to shift it left, then the content of this bit, last bit, will be moving to the previous one. Okay, 1. This one is going to move here, 1. This is going to move here, this is 0. This is going to move here, it is 0. This one is 1. This one is 0. This one is 1. And this bit will be discarded. Okay, so this bit is discarded from the input data. At the output, we are getting the data in all the bits, all the locations, but in the LSP side, here this is the LSP side, there is no data to be moved in. So by default, we will be moving in here as 0. So this is called the logical, this is called logical left shift. So whenever there will be a vacancy will be there, we will be filling that vacancy with 0 in case of logical right or logical left shift. So I hope it is clear to everyone. So next we will see is another type of shift,
Yes,
that
sir.
is arithmetic shift, arithmetic right shift and arithmetic left shift. So in case of arithmetic shift, we will be considering the part of sign bits also. So in case of flag or status register content, we have seen different type of flags are there. Flag registers are there. So basically the flags are of like carry flag, sign flag, or zero flag. So we have seen in the previous classes also. So similar to that, in case of arithmetic shift, along with shifting the bits of the register, we will be shifting the content of the sign bits also. Okay, so here we can just consider here, suppose an example we are taking is this one. Suppose 0 1 0 1 1 0 0 1. So this is the normal register that is given. We want to shift it arithmetic right shift. We want to make it so arithmetic right shift. So along with this, we are going to shift the data to the right side. Okay, so to the right side. So whatever the data is there, along with that, we will be including the sign bit also. These are the sign bit. So suppose for sign bit it is 1 is stored in case of sign bit. So now we are going to move the content to the right side. Okay. So when we are going to move the content to the right side, we will be moving this one. So this data will be moved here, 0. This one is here. This one is here. This one is here. 1 is here. 0 is here. And this 0 will be coming out here. And this 1 will be discarded. But the only difference between these two is instead of putting 0 here, we will be putting it like the sign bit content. So whatever the sign bit content is there, we will be making it here. So it's like, first of all, the sign bit of this content is whatever this register content is there will be a sign bit. So this sign bit here and here will be the same. So here it was 1. So again here also it will be 1 only. But because this is, if sign bit is 1, it is indicating like this number is a negative number. If sign bit is 0, that means the number is positive. So if a negative number is there, it should remain negative even after the shifting. Okay, and its magnitude should not be changing. So what it basically does is it includes the same sign of the sign bit, but it will be including in this vacant position, it will be including this sign bit itself. So it will be a sign bit and this sign bit will be copied to here. Okay, so basic difference is here no sign bit including is there. Sign bit is not included basically. In case of arithmetic type of shift, sign bit will be included and sign bit will be placed where the vacancy will be created. Okay, in case of right shift, this is the arithmetic right shift. Next we will see is arithmetic left shift. So in case of arithmetic left shift, along with that we will be having the sign bit also. So suppose sign bit content is 1 and here is 1 and the content of the register is, suppose this is the content and we need to shift it left side. So it is arithmetic left shift. So for arithmetic left shift, we will be shifting the data to the left side. So this one will be shifted to this location 0. This is 0. This is 1. This is 1. This is 0. This is 1 and this is 0. Okay, so this is how it should be taking place. And this 1 that is there, that we will not be including. Okay, but in the backend whatever there is we will be including here. So here we will be including the 0 and whatever the content of 1 is there, that will be discarded. So this 1 will be discarded and whatever the content of sign is there, that will remain the sign itself. Okay, so just to see between the arithmetic left shift and the logical left shift, both are the same. So in terms of arithmetical left shift and arithmetical logical left shift, both are same. Only sign is indicated here, but there is no use of sign in case of arithmetic left shift. So the basic difference between the arithmetic logic will only be reflected in terms of arithmetic right shift and logical right shift. There, the use of this sign bit will be there. But in case of left shift, there is no use of this sign bit. So the meaning of arithmetic left shift and logical left shift will be the same. It is equivalent to arithmetic left shift. So this is about the left and right shift, arithmetic and logical one. Next one is rotate. So we will see is the rotate. So in case of right rotate and left rotate. So we will just see what is left and right rotate. So here, once we are rotating it like right rotate is there. So whatever the content of the register is there, it will be rotated, means it will be rotated to the right side. So this will be moved to here, this will be moved to here, and this content of the LSB, instead of being discarded in the left and right shift, this will be rotated and move to the this location. So it will be like 1 will be shifted to 0 in this location. So it is here. After shift, it will be like 1 will be shifted here, 0 will be shifted here, 1 will be shifted here, 1 will be shifted here, 0 after 1 shifting here, 0 will be shifting here, 0 will be shifting here, and 1 will be shifting here, and this 1 will be shifted to the MSB side. So here, so this 1 will be shifted to MSB side. So this will be the answer after rotate right. Similar to this, if rotate left is there, only difference is we will be moving the content to the left side. So here moving left means we are going to move the content to the left side, and then whatever the data available here at the end, instead of being discarded in the previous cases, it will be moving to this location. So after the movement to the left side, the content will be 0 will be moved to this location, this 0 will be moved to here, 1 will be moved to here, this 1 will be moved to here, this 0 will be moved to here, 1 will be moved to here, 0 will be moved to this, 1 will be moved here, 0 will be moved to here, and this 1 will be moved again to the LSB side here. So this is the left rotate basically. So right rotate and left rotate. So rotate means the sense like rotation will be taking place in the circular path. So like it will be moving the last one, instead of discarded, it will be moving to the vacant position. Okay, similarly in the left side, it will be moving from the LSB to MSB. MSB bit will be moved to the LSB side by completing the circle. Okay, sometimes we will be using like rotate with carry. So some of the instructions are there that are going to use rotate with carry. So with the carry, in that case, instead of rotating here, we will be having another. Just we will see like if we want to rotate, suppose with the carry we want to rotate. So whatever the content of carry is there, So in case of normal rotate, carry plays no role. But in case of rotate with carry, there will be a role of the rotate carry bit. So here, while rotating right side, this carry will be taking part. So here, whatever the content, suppose 0 of the content, content of the carry is 0. Okay, then this content will be moved to this way, okay, at this location, and this will be following. At the end, will be like whatever the content is there, that will be moving to the carry. So this is how the rotate with the carry takes place. So we will see once we will be moving further. So similarly, in case of rotate left also, the carry can be included. The next one is conversion. So there are different types of conversions are there. So binary to decimal conversion, okay, and decimal adjust accumulator. Some instructions are there. That instructions are basically built to convert binary number or BCD number to decimal itself, decimal equivalent. So in case of 8085, one instruction is there that is called DAA. It is called decimal adjust accumulator. Its meaning is like this is called decimal adjust accumulator. So its meaning is like whatever the content of accumulator is there. Suppose content of accumulator is 0 0 0 1 0 1 1 1 0 0 1 1 1 0. So basically, this decimal adjust accumulator is basically used in case of like when we want to convert a BCD number to decimal number, or if BCD represent in case of BCD representations is binary coded decimal. So each bit is represented in terms of 4 binary digits. So 0 will be represented by this, 1 will be represented by this, 2 will be represented by 0 0 1 0, and so on up to 9. So 9 will be represented by 1 0 0 1. After 9, the 1 0 10 will be represented by, instead of representing with 4 digits, it will be taking 8 digit to represent. So in binary BCD number, 10 will be represented by 0 0 0 1 and then 0 0 0 0. So each bit after up to 9 BCD number is defined. 1 0 is there, then it will be represented by 1 separately with 4 bits, 0 separately with 4 bits. So similarly, if the content of the accumulator, suppose this is the content of accumulator, so it is not represented in BCD format. So to convert this bit into BCD format, a direct instruction is given, that is DAA, decimal adjust accumulator. So it will be adjusting the accumulator to convert it into the BCD format. So similar to that, based on the different architectures, we will be having binary to decimal converter or different converters instruction directly given. So these are the basic conversion operations. So in case of this to be converted into BCD, whatever the content is there, if it is 9, it will be remaining the same. If it is greater than 9, we will be adding 6 to this number. We will be adding 6 to this number because this is greater than 9. So we'll be adding this 6 to this number. So it will be 0, 1, 1 will be 0 with a carry 1, 1, 1, 0 with a carry 1, plus 1 is 1, 1, 1 is 0 plus a carry here. Okay. And again, this number will be coming out to be number greater than 9. So again, we will be adding 6 to it. So it will be 1, 1, 1, 1, 0. It is 1, 1 1 1 1 0 1 1 1 is 0, 1 carry is there, 1 1 is 0 with a carry, so carry will be remaining here. So it will be like this 4 bit will be a number that is 4, this will be the 3, and this is 1 is there. So in BCD it will be this as 1. So this number will be converted to BCD like this. So 134. So this is how different conversion instructions are there. That basically is defined into the different type of architectures. So input and output. So these are maybe specific instructions. So input output instructions we have already seen. In and out instructions. In and out instructions we have seen. Maybe done using data movement instructions, memory mapped. So here basically memory mapped instructions are there. These are basically memory mapped. So between input and output devices, data will be transferring to memory side. Okay, may be done by a separate controller. So here the input operations can be done in terms of the DMA operations. In case of DMA used, these input and output operations are basically used. System controlled operations. So some privileged instructions are there that is basically used by the system itself. So these are called system control operations. CPU needs to be in specific states to use these control instructions, and for operating system use only. So these control operations are instructions that are meant for controlling the operation of the CPU is basically will be used by the CPU itself. The user cannot use that instructions. So we will see some of the examples. Okay, transfer of control. So in terms of transfer of control instructions, here branch instructions, skip instructions, and subroutine calls are the different instructions. So branch instructions are there, like there will be some conditions. So first of all, if B is written, B move to 0010 location. That means whatever the, suppose there is some instruction add A comma, instead of A we are writing like R1 comma R2. Then this instruction came, and this then another instruction is like move R2 comma R2. So suppose this is the instruction. So once the CPU is going to execute this instruction, so execution of this instruction will be with respect to its address. So this will be saved into a memory. So in that memory, these instructions are saved at a particular location. It will be having some address. Suppose 1012 is the address. So based on that, what this is a two address instruction is there. So 1012 13 will be used for storing this. So this will be 1014. Again, it will be two address. So 1014, 1016 will be there. So these are the different locations where this instruction is used. So once the CPU is going to operate, the program counter content will be 1012. Okay, so this instruction is being executed. So once it is executed, next program counter will be incremented by 1, or whatever the instruction type is there. It is two address type, so it will be increased by 2. Okay, or the next program content will be like program counter content 1014. After that, it will be 1016. So once it is moving to 1014, it says like branch to this location. So into this memory itself, suppose at this location, this is the location of 0010, and at this location there is an instruction of subtract R1 comma R2. So once this is executed, after that it will be moving to this location. It is saying to go to instruction that is stored at this location. So at this location, this is the instruction. So it will be executed. This one is executed first, then this one executed second, then it will be moving to this location. It will be executing with third. After executing, it will be returning back here and then execute the move operation. This is fourth one. So once it is executed, first one, it will be executing second one. After second one, the next is this one. But the program will, the CPU will not be switching to this location, because this is going to have a branching to a location that is 0010. So at this location, now the CPU will go for operation. So first one, this one, second one is this one, third one, this one. After completion of the program stored at this location, it will be moving back and then moving to here. That is the fourth instruction. So here, this was the regular trend, but there was a branch instruction. So it is going to move into a branch and go where another instructions are stored. So it will be after executing, it will be returning back. So it is an branching instruction. So these are the branch instructions. So we'll take some examples also in the further class. Skip instruction is there. So here it says like increment and skip if 0. So some conditions will be there. It will be like if skip is there, we will be making a condition like increase, and skip if 0. If a particular register or a particular condition is 0, then skip the content. ISZ register 1. Its meaning is skip instruction if 0. It is like ISZ stands for increase and skip when register 1 is 0. So it means when register content is 0, then it will increase and then skip. Okay. So if it is not satisfied, if it is not equals to 0, it will be not be executed. It will be moving to next one. If a branch instruction is there, branch with some address is there. It is like add A. Then after that means this is how the branching is basically done. Some subroutine calls are there, like subroutine calls are called interrupt calls. So in between some instructions, there is an interrupt came. So interrupt came with some address. So again, like a branch, instead of going to this location, it will be going to the location of the interrupt. At this interrupt location, suppose interrupt location is this one. At this location, whatever the instructions are there, it will be executing, and then it will be returning back. So all this set of instructions are called interrupt call, or these are called subroutines. These instructions that will be located at a particular location. If a program is executing continuously, in between it is moving to a particular another location away from the main program, it is called the subroutine programs. So these are called subroutine calls. So here call, another call instruction is used. Suppose after move there is a call instruction, and it is saying like move to address this. So this call will be moving to this location now. So after execution of movement, it will be moving here and then returning back. And then suppose another one is R add R3 comma R1. So this is 1017 1018. So after execution of movement, it will be moving to 17 will be moving to here. After executing this complete, it will be returning back, then performing the add. So these are called the subroutine calls. So call or skip or branch can be used for branching or taking the control or transferring the control to a particular location. So some example is given in terms of the branch instruction still. So we will see this content into the next class. Okay.